Hi everybody, my name is Jewel and this is my interactive advanced concept presentation where we'll be making some ferrofluid. So going over the basic materials, we need some black ink toner, got some vegetable oil, and then I've got a scale to measure out my toner, a tablespoon, something to stir my toner with, and then most importantly, some really strong rare earth magnets. So hopefully this is strong enough. I got it on Amazon. It said it was super strong. So we will see. All right, so we're gonna measure out 50 milliliters of our expensive ink that we're just wasting. All right, Jesus. Okay, now we're gonna measure out 2 tablespoons of vegetable oil. And then we're just gonna mix that together. And we're looking for a liquidy mixture. All right, as you can see, it's pretty liquidy. Hopefully you can see that. All right, now it's gonna be the test. So I've got a rare earth magnet right here. There's 2 in here, so I'm just gonna separate them. I think I'm gonna mix it a little bit more. Yeah, I think this oil is gonna separate anyway, but. Okay, that's looking better. Okay, now I'm gonna take, oh no, it got on me. And what do you know? Does not work. Awesome. Yeah, so I don't know, this was supposed to be a really strong earth magnet. I'm not even seeing any spikes or any of those like little tiny nanoparticles picking up the magnetic field whatsoever. So, I mean, this is obviously strong-ish. Like, I don't know. Okay, whatever. So what is ferrofluid? Ferrofluid is a colloidal suspension. It's a liquid that displays a strong reaction to a magnetic field when it's present. It's a unique material that can act like a magnet, like a magnetic solid as well as a liquid. So this is because ferrofluid contains tiny magnetic nanoparticles that are suspended in a carrier fluid. The nanoparticles are typically magnetite or iron oxide, which is Fe3O4, and those are going to be coated with some type of surfactant that prevents them from clumping together. The nanoparticles are small enough that they're able to be suspended by the magnet without settling due to their weight, hence the name nano. The carrier fluid is some type of liquid like oil or water, and then this allows the nanoparticles to move freely when there's no magnet present. So like right now, no magnet present, it's gonna act like a liquid. When I introduced the magnet, it was supposed to act like a magnetic solid to a certain extent, and you should be able to see the nanoparticles like rising up with the magnetic field, but obviously it did not work. Let's see, where was I? So when this ferrofluid is exposed to some type of magnet, the magnetic nanoparticles react and align themselves with the magnetic field lines. The field lines are actually what we would be seeing when we see that ferrofluid creating the spikes or the patterns. The ferrofluid's response to the magnetic field is a result of the competition between the magnetic forces that are acting on the nanoparticles and the thermal motion that wants to keep them dispersed. So this magnetic reaction only occurs when there is a magnet present. When the magnet is removed, the ferrofluid will immediately return to its original form and behave like a normal liquid, which has a random orientation. So this characteristic of the ferrofluid is considered super paramagnetic since the magnetization is dependent on the presence of a magnet, and it's distinct to ferrofluid when it's in a nanoscale. So ferrofluid has different applications in the real world outside of a chemistry lab. So it can be used in rotary seals in computer hard drives and other rotating shaft motors. It's also seen in loudspeakers to help dampen vibrations. I think that is probably what we're most familiar with. And then it also has a place in medicine where it's used as a contrast agent in MRIs. So ferrofluid's a really interesting material that allows us to visibly see magnetic reactions in the fields. Unfortunately, it did not work for me, but I think I have an understanding of what it was supposed to look like. So, all right, thank you for watching.